Thanks everybody for coming. My name is Nick Whiting. By day, I'm a tech director at Epic Games, and by night, I work on standards like OpenXR. I'm actually the working group chair, and today I have the privilege of presenting the work of a really talented group of folks and give you guys a first look at OpenXR, which is what we jokingly refer to as standardizing all of the realities. So the agenda for today, we'll give you a quick note on what we'll cover and a few provisos, since this is a kind of pre-release preview of a spec that is still very much a work in progress by a lot of very talented folks and companies, a few of which are in the room today. I'll give you a kind of a brief history of the standard. We kind of announced it at the beginning of last year, so I figured I'd let you guys know what we've been up to, hard at work, trying to converge on getting something out there. Then kind of an outline of the problem that we're trying to solve with OpenXR and the things that we're trying to address. And we kind of made a few philosophies as a working group that help inform what we should concentrate on, what we should move on from, what we should just not even touch at all because it's too early. And then the part that everybody's probably actually waiting for, I'm going to give a kind of high-level overview of a good bit of the standard. We're not going to present any specification, specific language here, but we should give you a kind of good overview of how the system works, what we cover, how it's extensible, and then I'll kind of address where we go from here. And at the very end, I figured there's probably going to be a lot of questions because this is the first kind of coming out party for OpenXR. So there should be ample time at the end of the presentation for you guys to ask any questions you want. So with that, a few notes on what we'll cover. So the first proviso is actually the most important, and this spec is still very much a work in progress. It's pretty lengthy already, I think 268 pages at last count. There's bits and pieces that are kind of in a flux right now, but overall the body of it is kind of taken shape, and that's why the working group felt comfortable talking to you. But that being said, all this stuff is still subject to change. Right now we're going through a period where we're starting to actually implement the spec ourselves. A few people in the group are, and like with any piece of software, there's bugs in it. So everything up here is not yet canonized as gospel truth, but we're hoping to get there before too long. So for this talk in general, we assume that you guys know a little bit about VR and AR and how it works at kind of a general level. A little bit about programming, and you can get your way around a render loop decently. But two things that we don't want to assume is that you know anything about the specification process, because I know I sure didn't before a year ago, and that you don't necessarily have any knowledge of other Khronos specifications. So we'll cover anything that should be new there. And as I mentioned, the spec is pretty lengthy, and we're not going to cover the whole thing. What we really wanted to focus on with this was just give you guys an initial preview of parts of the specification that are mostly well-defined at this point, and we felt comfortable kind of talking about it at a higher level. But there are entire systems that we aren't going to cover in this talk, and we'll have to wait till the release of the spec in a little bit. And as I said, there should be plenty of time for questions in the end. The kind of provisos with that are I can't answer any questions about systems that aren't stabilized, and no, you can't ask when it'll be released, but I'm sure one of you will, because that's how it always goes. All right, so a brief history of the standard. So it started about a year ago, but the standard is really comprised of a whole bunch of companies that when we first announced the standard, people were like, how are you going to get these people to work together? There's no way that company X will join in a standard with company Y. And as you can see from the images up there, that's not even all of the people that are involved in the spec. These are the people that were willing to put their logos up at this early stage. But you can see that OpenXR has kind of successfully got dogs and cats to live together in harmony. A little bit. Epic is up there with Unity, and Oculus with Valve, and it's actually been really great and very collaborative. I think that's one of the things that's impressed me most about the entire effort, is that everybody wants this thing to succeed, and so everybody's willing to work very hard and very cooperatively on some thorny engineering issues. So it's been very refreshing. And I think, if nothing else, the takeaway from this talk is that OpenXR has legs because of the participation of all these companies in here. And a lot of them have publicly committed to adopting the standard in the very near term. So keep that in mind as we go through the rest of this. As for a brief history, as I mentioned, last year was kind of our our initial announcement of the exploratory group. We sent one of our members, Joe Ludwig from Valve, on a lightning quick day trip from Seattle to Korea to propose it to the technical advisory panel and see if there was an interest in it. Unfortunately, there was quite a big interest, so the group started generating a statement of work, basically deciding what should we put in the spec, what should we try to put in the spec, kind of thorny issues like should it be a VR and AR spec, should we do one or the other and then save one for a later version. We kind of got that all sussed out, and then we put out a call for participation. And actually, right over there, last year, we had a panel that kind of announced us as an official working group, and we kind of began work there. We started kicking it off at the Winter Face-to-Face January a year ago in Vancouver. And it was nice because we had 3 or 4 different companies that came up and actually proposed specifications as a starting point from it, because that was one of the things we wanted to have kind of a straw man proposal in order to kind of suss out some of the technical issues. And multiple members of the working group actually put up fully fleshed out specifications for it. So we had a good starting point, and we kind of unanimously approved picking Oculus's contribution, which was at the time called Etna, to be our kind of starting point. And that was based on their work on merging their desktop Rift API and the Gear VR API. Over the next 2 face-to-faces, we started actually working on chopping up the spec and just kind of doing the heavy lifting, you know, take the car apart and get ready to put it back together on the garage floor. There's a face-to-face in Amsterdam. We do them quarterly with Khronos, but there was so much work to be done that we actually decided we needed an interim face-to-face to get together and kind of suss out some of the language. So we did that in July last year at Valve's offices in Washington, before our big kind of next milestone, which was last fall's face-to-face in September in Chicago, where the working group was like, okay, we've kind of talked about this enough. We really need to start chopping things down and deciding where we're going to plant our line in the sand in order to define an MVP product. So at Chicago, we had a lot of fun deliberation over a long list of bulleted points on what would be MVP, what would not be MVP, who cared about what, was anybody willing to stand up and propose a feature. So we had a pretty good idea as of last fall what was going to be in the final version of the spec. And again, we had more face-to-faces quarterly, but we had so much work to do, especially after defining what it wasn't in the first version of the spec, that we ended up having another interim face-to-face at Valve. And basically, at Taipei in January of this year, we said, okay, now that we've defined this MVP, we want people to start actually implementing the runtimes that adhere to the spec and make applications that adhere to the spec so that we can start sussing out the kind of last-minute bugs with it. And so at Taipei, we kind of sussed out the last issues for that, and now people are actually starting to implement and run OpenXR compliant runtimes and applications. And here we are at GDC right now, right here, and you guys are getting the first look at the specification. There's some stuff that's coming in the future, which I'll cover at the end of the slide, but that's kind of our history up until this point. Now on to kind of goals and philosophies of the specification. So the problem space as we see it with OpenXR is that the ecosystem right now for VR and AR apps kind of looks like this. You have a whole bunch of applications, and they either integrate directly with a bunch of runtimes that are proprietary per company, or they go through an engine, which then has a bunch of plugins or some other systems to connect to those APIs, and then all those APIs kind of connect to their own devices. And what that leads to is a lot of kind of market fragmentation. The VR and AR market right now is pretty small. And if you're an application developer, you need to hit as large of that addressable market as possible. So that implies that you've got to either integrate with all these different kind of runtime targets, or you have to use an engine that does that for you. So part of the motivation for OpenXR was very selfish in that I run the Unreal Engine XR department, and I wanted to save myself work, so I tried to get everybody together to make one single specification. But this also kind of presents a problem from the other end of the slides, in that if you're a hardware manufacturer or you have some sort of specialty peripheral, it's very hard for you to convince application developers to support your peripheral, because that implies more work and more engineering effort and more cost for them. So people that make new peripherals and whatnot end up kind of getting lost in the noise a little bit, because it's very hard for them without just throwing money at application developers to get them to integrate into their ecosystem. So the solution, as the OpenXR group sees it, is to create a OpenXR standard that has kind of 2 faces. One is a application-facing specification, and one is what we call the device plugin extension on there. So the application-facing API is an API that all runtimes have to implement, and that's what allows the applications to talk to the OpenXR runtimes. On the other side of that coin is the plugin extension, which basically lets arbitrary devices kind of talk to OpenXR runtimes. And that's really the magic that lets one runtime talk to a bunch of different devices and really opens up the ecosystem. So we think that a lot of people will end up implementing runtimes, and we hope that a lot of them will actually implement the device plugin extension to make their devices cross-compatible with all the other runtimes. So the kind of flow is that the application does its rendering, sends its imagery down to the OpenXR runtime, and the OpenXR runtime processes that. It handles composition, handles distortion, handles sending out haptic events, and then presents that to the device. And at the same time, it sends tracking information up from the runtime for the devices and input information up to the application. So as far as the application is concerned, it's kind of a single target that it has to aim for. And to help us with these goals, we kind of decided on 4 philosophies as a working group that help kind of guide what we decide to work on, how we frame those APIs when we work on them. The first one is that we really wanted to enable both VR and AR applications. Basically, the X in OpenXR started as a joke on a PowerPoint when we said if we put a V on top of an A, it makes an X. And that was really about as much thought as was put into it. And everybody just kind of liked the idea. And it was one of those things that was kind of so stupid it worked. But if nothing else, we wanted to really kind of clean up the ecosystem of MR, XR, AR. There's some other Rs that are coming out now. We said XR is a good kind of catch-all term for that. What we define XR as something that has real-world sensor data that's being fed into a device. Whether or not that device displays or anything is kind of up to the runtime, but we really wanted to make a common API that unified a lot of those concepts that are common to all XR devices. The second is that we really wanted to be future-proof. So the first version of the spec, OpenXR 1.0, was kind of focused on current devices and near-term devices. But the standard is really built around being extremely flexible so that you can not only target those kind of current devices, but allow future innovations and developments to kind of be gracefully folded into the ecosystem. So when I talk about a lot of these things, they have expansions where if you pass in a struct, there's ability to pass in more data as kind of payloads, very similar to how Vulkan works. You can have extensions to the API, just like Vulkan, and what we really wanted to do was make sure we don't paint ourselves out of any corners of precluding any type of device coming in. Kind of along those lines, we thought it would be pretty foolish of us to kind of try to predict the future of XR technology. I mean, if you've been following AR and VR developments in the past few years, you've noticed that there's nothing if not a lot of crazy, wacky ideas that want to kind of find their feet. There's kind of the standard devices that are in there that are either 3DoF or 6DoF. Now we start to have inside-out tracking versus outside-in tracking. But what we really wanted to decide was, we don't know if somebody's going to make a crazy shoe-based controller that's going to be something that, catches on and is actually super cool. So what we wanted to do was make the API as flexible as possible, kind of codify the concepts that are unique to everything, but for things like input and display timing and whatnot, make those very extensible so it's easy for people to kind of drop in. And number 4, which is one of my personal favorites, again, as an engine developer, is unify some of the performance critical concepts in XR application development. So if you target even 2 similar devices, like an Oculus Rift versus a HTC Vive with Steam VR, things like frame timing are done subtly differently, but in a way that really makes it hard for our engine's render pipe to kind of adapt to it. So one of the things that we really wanted to settle on as part of OpenXR was how do we take these things that affect device performance and make them codified so you can at least build to one kind of pattern of a target, even though there's no promises that without content modification you can make something that runs on a really badass gaming rig run on a mobile phone. That we don't try to do that. But what we want to do is make sure that the performance and the timing of your render pipe is similar across both platforms so that you can kind of target and optimize your content to one and know that it's going to be a reasonably good approximation on another. Now, in order to do that, there's kind of 2 approaches to runtimes that we think people will take. As I said, if you're an OpenXR compatible runtime, you have the OpenXR application layer so that applications can talk to your runtime. But one of the things that was important to a lot of the members of the group was that they didn't necessarily have to support multiple plug-in device extensions. And there's kind of 2 reasons for that. One is that some platforms, some mobile platforms especially, have very strict security requirements, and it's not always possible to load in drivers that are required for them to kind of abstractly support a device plugin. The other one is there are some, economic considerations here where, exclusive content may not want to work on all devices, but we still think that it's important for the application developers to be able to target an OpenXR runtime, even if they have to have multiple runtimes on the machine. It still means that the application developers can target kind of a single specification. The other side of this is runtime B, which actually implements the device plugin extension layer. And what that means is that that runtime handles composition, but what it passes off onto devices, it can take arbitrary devices in. So maybe it works with an Oculus and a Rift and a Google device, or some other kind of more specialized or bespoke hardware. We hope that a lot of people kind of integrate the device plugin extension because we hopefully have made it flexible enough that it shouldn't preclude any sort of device from being integrated into the ecosystem. One of the other big things, if you're familiar with Vulkan, you know that Vulkan is a layered API. We wanted to make sure that OpenXR took the best parts of Vulkan, cribbed off of their cheat sheet a little bit, but it's a layered API. So if you look at the application, looking at talking to the application talking to the application layer, talking to the runtime, where you see those red lines are where you can actually insert layers into there. And what layers do is instead of the application calling directly into the runtime, you can kind of shim function calls into the middle. So it's useful for things like debugging information that you don't want to necessarily have at runtime, but it's useful as you're developing an app. The nice thing about it, using that as a layer, is that you can easily just turn that off and not run with the penalties that you would have to pay for it to record extra information about the state of the system. There's also verification layers that you can insert to basically for an application to check, am I using the API right? Am I calling these functions in the right order? Did I do something incredibly stupid? You can help catch those without paying that runtime performance penalty. Another interesting one that we think will come up is performance and profiling layers. There's a lot of interesting challenges with AR and VR apps revolving around timing, and being able to insert a layer into there, then get that timing information and kind of visualize what's happening when you miss a frame, for instance, we think will be very useful. So this is a core part of the API that we enable. With that, we'll get into the standard itself. So the first thing I want to go over is some of the kind of conventions and primitives that we use in OpenXR. So for objects that are kind of allocated by the runtime on behalf of the application, we represent with handles. These aren't reference counted handles, so you have to be careful because the application itself manages the scope. So they're kind of opaque to the underlying object. You can't, query a handle about the instance and say, what's your internal state, but you have to pass these into a lot of the functions because we are a C-style API. Generally, the lifetime is managed with create and destroy, so as the application goes in and out of VR or AR mode, it can create and destroy handles as needed, or if the instance needs to update under the hood, you can destroy the handle and allocate a new one when you're ready to go again. One thing to point out about this is that the handles are hierarchical in a lot of cases. So as we'll get to in a few minutes, we have an instance which is kind of the application's view of the runtime. And within that instance, we have a system which represents the devices that you're actually using in the runtime. So instances are only valid for their parent handles, and there's a couple other things like input that are only valid within the scope of their parent. And we enumerate those, again, for extensibility by using an XR object type enumeration. So we hope we can slot in new ones as extensions need to. If you need to add a handle type, it's there for you. You just change the object type. Another one of the core concepts of the API that's really aimed at helping with forward compatibility and versatility is what we call semantic paths. And these are a concept, I believe, that was introduced with VRPN. I'm not sure, but the folks from Sensix, which make OSVR, have used this for a long time in OSVR, and we thought it was a pretty good concept, so the group ended up adopting it. So a semantic path is basically nothing more than just a hierarchical string representation of something in the XR ecosystem. So we'll cover exactly what these things are in a little more detail later, but things like spaces, which define kind of basis spaces for the application are in there. Different devices, if you have a controller and the controller has buttons, those can be addressed by semantic paths, as well as viewport configurations, which is how many eyes do I want to render, basically. If you look at them down at the bottom, they're very much like your standard kind of file path handles. They're hierarchical and let you kind of address arbitrarily long hierarchies of objects in there. The properties of them, as I said, they're hierarchical, but one of the most useful of them is that they can be aliased. So user representation is one of the things that we use for semantic paths. So you have a user and he has a hand and he has a left hand. But also you can address these with alternate semantic paths if you wanted to say what's the user's primary hand. If in the runtime they've selected I'm a left-handed, I'm a right-handed individual, we can alias user hand primary, and so applications can say whichever hand that they're using as their primary hand is the one I want to give them UI hints on or let them use the point the gun with or something like that. They're stored in a string table, so they're not horrifically slow after you kind of define them. The human readable, which is very nice for debugging. They can be predefined. We have a number of reserved slots like the user hand left and user hand primary. But you can also define them at an application level. If you want to create new spaces or something, you can define meaningful full paths to those kind of data types for yourself. They're treated as handles, so you manage the lifetime of those. Case insensitive with kind of your standard value characters with a null terminated string. But the one thing we're always careful to point out is that they're actually not file paths, so you can't use kind of dot and dot dot to go up and down the hierarchy. For the reserved semantic paths, here's a couple kind of classifications of them. The user hand and, left and user hand right, which can also be aliased with user hand primary and user hand secondary based on the runtime's user profile of that person. The head is a reserved semantic path, but also the device layer. So devices that are providing input or display capabilities, you can register with your vendor name and your device name and your identifier and component, and then build out a tree of kind of an arbitrary construction that helps define exactly what kind of input your device provides and what kind of output it can take. The next concept is the XR space, and this is kind of one of the fundamental concepts used throughout the API to help make it generalized and able to work on AR and VR, inside-out tracking and outside-in tracking. So at kind of a fundamental level, we have a right-handed coordinate system that you can see in the top right, but within that coordinate system, we define a lot of spaces. Which is basically just a basis that returns kind of a translation, a location, and a scale within that space. The runtime basically has an internal representation that it can store however it wants to. So it gets tracking data from one source or multiple sources. How it stores the representation internally is up to it. In cases like an Oculus or a Vive that are outside in tracked, that world space is probably pretty static. But in the case of AR or inside-out tracking headsets, that state is always kind of malleable as the mapping defines more places that it recognizes. So the way we kind of get around those sticky issues with OpenXR is that we let you define spaces like a floor plane or an eye-level plane, but then we define a function that lets you get the relation between any two of those spaces. And those spaces can be continually updated, as I said, if the room is discovering more about what the layout of the actual room is, it can adjust those as it's needed. Or if you wanted to attach a tracking space to a motion controller, for instance, and have that basis function kind of move along with the motion controller itself so that you can attach things in relative space, you can do that as well. So this is kind of the overall structure of the instance, the system, and the session. These are the kind of the three base level concepts of OpenXR. So first of all, you need a loader in order to get a handle to one of the runtimes. So an application basically says, hey, I'm an OpenXR application, I want to use OpenXR, I need to find a runtime that's compatible. And we're not requiring you to use the OpenXR loader that we ship, and we imagine that this is one of those things that will vary in complexity. You can either have one runtime and just use that all the time, or we might have ones that let you pick, the user pick intelligently between them based on what hardware is plugged in, which apps are running, if you have a kind of home baseline experience. All those factors can be taken into account. The reason that this one is a little bit more malleable too is that some platforms like Android have very, very specific requirements about what this loader is allowed to do. And so we try not to put too many restrictions on it and leave it open-ended. Basically, as long as it can pick a runtime for you and return those handles to the application, that's all it needs to do. The next thing in the hierarchy is the XR instance, and this is really, the application says, I'm an OpenXR application, I need a handle to a runtime, and that's the XR instance. So we use this function XR create instance to ask the loader for a hook to a runtime. And at that same time, we can also pick if we want to enable any debug or any layers or any extensions at that same time. It's very similar to the Vulkan initialization path. So the application is like, hey, I'm ready to go. I need the extensions for Vulkan potentially. Give me a runtime that's compatible with that, and then it returns a handle to that runtime, which we then use to do the rest of our OpenXRing. The next level in that is the XR system. So the XR system is essentially a group of devices that work together within OpenXR. So you can imagine an HMD and a set of controllers comprise an XR system. They have different capabilities. Some of them can display, some of them can track 3DOF, some of them can track 6DOF. But all of those are kind of represented as a system. So the first thing you do after you create an instance is you ask the instance, what hardware do you support? And then it gives you a list of that, and you can pick, I want to run on this system. So basically, when you enumerate the physical devices, you get a few of the properties about them. One of them is what kind of tracking they have. Other ones are what resolution are they capable of supporting, if they can support MSAA, what their swap chain length are, what kind of input devices they support. This is also kind of the part where we need to start caring about what graphics API is, because the system is responsible for allocating swap chains, so we need to know what kind of swap chain textures you need to use. There's actually some special extensions in here for Vulkan, because potentially you might need, some of these runtimes might need specific Vulkan extensions enabled, so you can query that at this time and then enable your instance with the Vulkan extensions that you need. Next up is a session, and until very recently, actually, this was another handle kind of lifetime object, but it's recently been demoted to just a function to begin and end a session. And basically, a session is how an application indicates whether or not it wants to render VR output at that time and get input from a tracking system. So it's pretty simple. Once the application is ready to start sending frame data and allocating its swap chains, it says begin session, and that tells the instance that, hey, this guy wants to start rendering frames to the device, we should give it use of the runtime and display on the device, and then when it's done, it can call end session. Basically, the rule here is if you haven't started the session, you can't give it frames. But this is nice for mixed mode applications too. If you have a AR application on a phone, for instance, you can start without a session but initialize all the OpenXR stuff, and when you want to kick it into AR mode, you just begin a session, and then you can start taking the input. When the runtime wants to communicate with the application, we do so through the events queue. So the events, here's a kind of a couple of them, but they're very basic and pretty extensible. The ones that are kind of fundamental to the system are visibility change, focus change, which is whether or not you are actually rendering on the device or getting input from the device system. But there's also a little bit more kind of heavyweight ones. If the runtime says, hey, somebody else wants to render on me, it can send a request that you end the session immediately so that you stop ending frames and yield to another application. Sometimes if the runtime has to update, it can ask that you end the instance and then recreate it later after it's gone through an update. But it also has some of the more kind of user-focused events, such as if the user puts on the headset or takes it off, or if the user trips over their cable and yanks it out of the computer and you need to handle that. Those are all surfaced through the event system. It's basically just a simple event queue that the game application is expected to pull at whatever rate it kind of updates its simulation at. There's no kind of restrictions on how fast those queue messages have to be handled. They just kind of build up until the application processes them. Next up is input and haptics. So the input is one of those things that we don't dare as a specification actually predict what it's going to look like, because we expect this to be a pretty crazy area in the coming years. So we go through an abstraction where we try to get the applications to define events that they care about, such as kind of I want to move, I want to jump, I want to teleport, I want to shoot a gun, rather than specifically binding directly to the controls. So a lot of games, you say I want to press A to jump and I want to press B to shoot my gun. We say shooting a gun and jumping are two actions, and we let the runtime actually bind which button on the device actually handles those things. Again, this is handled completely by the runtime, so we expect if you boot up SteamVR, for instance, you'll have a bunch of controller bindings, and then the user will be able to kind of pick which ones they want. And this has kind of several advantages by forcing that abstraction. One of the things is one of our group members, Joe Ludwig, said that dev teams are ephemeral, but platforms are forever. And that's kind of a jerkish thing to say because he's a platform owner, I'm a dev team. But I think the sentiment is correct in that, especially right now, people that are making applications and whatnot, it's 1 or 2 years down the road, it's very hard to go back and actually get a system that can compile and find all the dev team members that know how it works to update those applications. applications, but the platforms tend to hang around for a much longer time. So by pushing this kind of binding to the runtime, if somebody comes out with a new awesome headset or a new awesome controller, and the runtime supports that, it can say, hey, if you have a gun peripheral now, you want that trigger on the gun to shoot rather than the A button, that leaves it up to the runtime. The runtime can update and map those new controls. So it's really a quite powerful tool to future-proof things. It's also interesting in that it kind of allows for mixing and matching of multiple input sources. So if you had a runtime that was combining maybe a Vicon tracking system with some other arbitrary display system, you're not bound to use whatever controller was created with the application. You can map those two together just as easily as you could any other. So it's very seamless to the application. It just gets the data. It doesn't care where it comes from. The runtime is what's mapping it for it. It also makes it pretty easy to support optional features. So if the OpenXR runtime potentially supports body tracking through use of trackers, we can say, hey, if you feed us data for where the left knee position is through whatever kind of tracking methodology, be that a Kinect or a Vive tracker, we can ingest that and then actually put it in there. And it's the OpenXR runtime's job to normalize all those spaces together. So to the application, it's just another source of input. And that's pretty darn cool when you think about all the kind of combinations that people are doing, especially for kind of location-based VR experiences. And kind of finally, it kind of solves that the right hand of that original problem statement where if I'm a hardware manufacturer, I have a cool new device that's a little bit novel. How do I fit that into the ecosystem, and how can I get content built upon that? With this sort of thing, if you say my foot controller provides kind of locomotion input for going forward and backwards, left and right, you no longer have to have the application developer take that into consideration. They can just bind that in the runtime as long as your runtime supports the hardware, and the applications automatically can use that. So the actions that I mentioned up there have a couple properties that I'll go over real quick. The first one is just kind of its identifier name, so teleport, jump. Nothing terribly interesting there, but it also has a localized name, which is kind of the human readable description that's surfaced in the UI of the runtime. So this can be the same as the action name for simple things, but it also might be something that is a little more complex to describe a more complex action. We also have action sets, which I'll get to in a few, but it allows kind of groupings of actions based on the different states that your application might be in. And finally, we have the suggested binding, which is if the user hasn't bothered to go through and actually configure what their input settings are for the runtime, they can, the application can provide a set of suggested bindings. So if I was making a game, I said, okay, I want this to be the default binding for using Oculus Touch controllers, and I want this to be the default binding when I'm using a Google Daydream headset. And the application can kind of provide those recommendations. But it's ultimately up to the user in the runtime whether or not they want to use those or not. There are some limitations on it. There's a couple different types of actions, booleans, one-dimensional vectors, which are kind of the scalars, two-dimensional vectors, and three-dimensional vectors. And through the use of those relative paths, you can kind of build hierarchies of this. So if you had a device input that could provide a two-dimensional vector, kind of like a thumbstick, you could bind that to a type vector 2f, and you have x and y input into there. But you're not kind of restricted to that. If the runtime is like, I want to take together these two completely different arbitrary joysticks and mash the left and right on this stick to the front and back on this stick, or if I want to remap a thumbstick input for a car racing game to a pedal, you can also do that custom in the runtime. There's one more kind of very special type of input, which is actually one of the things that's being debated as of kind of last week and this week, which is the XR action state pose, which is basically just saying this action input is something that has a full pose and that it has a position and a rotation with it. And it could potentially have other inputs such as linear velocity, angular velocity, and accelerations into there. You can pull these in the same place you pull all the other input actions by calling XR get action state pose. And then it passes back a flag to say, hey, these are the parameters for it, but this controller is only 3 DOF, so it doesn't really support a position bit, for instance. Again, this is really kind of designed to be generic and flexible so that as new devices come on, you can map them into the runtime pretty naturally. Action sets are kind of what I touched upon before, but if you have an application that has kind of different modalities of interaction, you can define different action sets and swap between them. So In our hypothetical example of Kitten Petter VR, which is a game I really wish somebody would make, you could be in potentially two modes. One is petting the kitten mode, where you want the A button to spawn a yarn ball for it to delightfully play with and be adorable with. The click might teleport you around the room, and then pulling the grip button might spawn you more delightful kittens to play with. But also, if you're in the UI for that application, you don't want to be able to spawn kittens potentially or spawn yarn balls. You want to be able to select items, change the menus, and scroll through the menus. And that's why you can have an entirely different action set that's devoted to UI mode. Again, these are optional things, but the more robustly that applications can actually define their action sets, the better that people can integrate new types of hardware and future-proof their applications towards devices that come down the road. And if you've ever made a VR or AR application, you know that users can sometimes be a little bit frustrating and just not getting what you had intended them to get. So sometimes you have to provide UI hints to tell them how to perform actions. So we also have a kind of a reverse lookup that you can perform with this, where you can say, hey, I want to tell the user that they need to pull the trigger to teleport. How do I do that? You can ask the OpenXR runtime, hey, what button on this device is actually bound to the teleport command, so that you can draw the controller in the actual application itself, or you can put some UI saying, hey, pull the trigger to teleport, idiot. And hopefully they get the hint. Haptics are something that's also in the specification that goes through the same sort of input action thing. Haptic actions can be in action sets, just like regular input actions are. But basically, this allows you to send vibrations out to the controller. This is one of the things. We have one baseline type of haptic action, which basically just has a start time, a duration, a frequency, and an amplitude, kind of based around current hardware. But this is one of the things that we expect as the technology improves, that you can use, that people will write extensions and vendor-specific extensions to be able to take advantage of more complex haptics. I mean, we have haptics now that provide shears against the palm to kind of make it feel like you have something in your hand as opposed to just vibration. All of those can be very easily slotted in through extensions just by defining new types of XR haptics. And if you add those to your haptic set, then as new devices come down the road, they might be able to make an intelligent mapping in the runtime between the information that the application is providing and the haptic device that they actually have. All right, so that was input. Now let's get on to a little bit of the rendering pipeline up here. So at a kind of high basic level, we have the three functions that everybody kind of knows and loves from current VR and AR applications. XR begin frame is basically what you call when you say, hey, I'm ready to start rendering. I need to get my next item in my swap chain and then issue a bunch of draw calls. So call XR begin frame, you make a bunch of pretty things to render on there. And then when you're done rendering and you want to tell the compositor, hey, I'm ready to take all these layers and then have you display them, you call XR end frame. Pretty simple. It takes a predicted display time and how many layers that you want to present. I'll kind of get into the details of that in a little bit, but it's very similar if you've worked with any kind of modern VR API on how that loop goes. The one that's a little bit special is XR wait frame. And this is called, and when it returns, it's a kind of a delayed function. When it returns is when the runtime says you should start simulating your next game frame. So Valve calls this running start. Oculus, I can't remember what Oculus calls it, but they have a similar sort of functionality that's supposed to gate you on how fast your application can render. And the idea is really the runtime knows best and when to release your application to start rendering so that it can position you to have your rendering work done as close to when the compositor is hooking and displaying the frames in order to minimize latency. XR wait frame, if you dig into it a little bit more, takes a swap interval parameter. And what the swap interval parameter does is say how many frames you want to wait for. So by default, swap interval 1 means every time the native displays refreshes, I want to render a frame. But you can also specify more than that. So if you say specify swap interval 2, XR wait frame kind of skips a frame. So if you want to render at half frame rate and have it do the reprojection under the hood, you can specify swap interval 2, and then it will be the runtime's job to upsample that to display at the device's native frame rate. If you try to specify swap interval 0, it's completely invalid, rips a hole in space and time. Don't try to do it. But basically, all in all, this XR wait frame is how the application gets throttled by the runtime. In order to make it a little bit more concrete, let's look at a frame timing diagram. So this is a very simple kind of DirectX 11 OpenGL style simple multi-threaded renderer that has a simulation thread that's responsible for updating the simulation of the game. It has a render thread which is responsible for generating a bunch of draw call commands and then sending them to the GPU. So this is actually easier if you start with the blue frame, or the kind of vaguely taupe, I guess, frame on 102. That frame is one that's kind of well scheduled, fits within the allotted amount of time. The simulation thread runs and then calls wait frame to wait until the next block of time, and then it kicks those jobs off to the render frame, the render thread. So the render thread does a little bit of initialization work, and then when it's ready to call actually start issuing GPU work, it calls begin frame, and then it calls end frame when that's done. If you then back it up to frame 101, the simulation thread you can see is coming very, very close to the compositor's hook between frame 100 and 101. Because of that, it knows that it can't actually make the next frame, so it decides to hold out for another frame, and the XR wait frame there holds for much longer than frame 102 does. So what this is really doing is the runtime is making an effort to get the application back on track and starting its work at a time where it thinks that the application will be done in time for the compositor to present. Now, this is a more deeply pipelined multi-threaded example. This is actually kind of how Unreal Engine does it. It's a little bit abstracted, so I know there are certain people in the audience that will probably disagree with my level of abstraction on it. But basically, Unreal has a simulation thread, which we call the game thread, which then calls the render thread, which starts to issue what we call RHI commands, which is an abstraction of the rendering API. And then the RHI thread starts to translate those into actual Vulkan or DirectX commands, whatever. So there's a layer of indirection within here that makes it a little bit more complicated. So this application doesn't have any missed frames, so you can see XR wait frame is pretty much firing at the same duration each time. But you'll see on the render thread, the kind of lighter versions of the diamond are when we enqueue the begin render commands, and then they actually get executed on the RHI thread when we actually start translating them into draw calls and work for the GPU. And then we have a little bit of a render thread fence over there where we say that the RHI thread can't get more than one thread ahead of the actual render thread. So the interesting thing, though, is if you look at the gray arrow there, we can actually have up to 3 frames in flight with OpenXR, and we just extend our swap chain slightly in order to handle that. So that was a very brief summary of something that took about 3 months of rendering programmers fighting in a room over a whiteboard to get, but we're pretty confident now that we've started implementing stuff that this solution will work for kind of future-proofing ourselves against, highly parallel APIs, as well as kind of work in the simple case where you just have kind of a simple render loop and maybe 1 or 2 threads working on it. In terms of actually managing the swap chains, it's a pretty simple system that if you've done any rendering programming, you should be pretty familiar. We create the swap chains based on the XR system. So we say, hey device, what's your native resolution? How deep of a swap chain can you handle? What should we do for recommended MSAA settings? You create a swap chain, and then right after that, you get a swap chain image, which is what actually gives you back handles to textures that you can render to. And that's based on which graphics API that you initialized in the create system. And after that, you can cache those textures for as long as the swap chain is alive. When you're in your actual render loop, you acquire a swap chain image, which gives you an index into the array of images that it gave you. It's important to note they're not necessarily in order. The specification says that they can be returned in any order, so applications have to handle that. Then wait swap chain image is a function that waits until that image is actually available for you. But if your swap chain is long enough, hopefully that shouldn't be waiting for you. You can go through your normal render loop, and then right before you're ready to call XR end frame, you release the swap chain image and say, hey, I'm done with that. And then it will use that in the next XR end frame. And then when you're all done with that, you call XR destroy swap chain, and the whole thing goes away. So as a kind of a quick reminder, we have a system that we call layers right now, but even this name is highly controversial. We jokingly named them after one of the members of the group, Cass's. If you're familiar with Cass Everett, he has the honor, I guess, of having layers named after him in a joking manner. But the compositor is actually responsible for taking all the layers that you define. So left eye, right eye, you can have some special layers like quad layers with UI in the world, and then aggregating those all together in XR end frame. The XR, when you give them to XR end frame, you give them the composition data, which kind of specifies a type, a display time when the XR runtime expects them to actually be presented, which eye they're associated with, if any, and what space they're in. So again, if you go back to the very beginning where you can define multiple basis spaces, you can do that with everything like compositor layers. So if you wanted to, for instance, have a quad layer that hovers above a track device or a motion controller, you can specify that as the space and just give it a static offset, and then the runtime will do all the math under the hood for you. So it's pretty slick being able to define arbitrary bases. The two most common types of compositor layers are the XR compositor layer multi-projection, which kind of is just basically your basic left eye, right eye stereoscopic one, and then the XR layer quad, which is the kind of quad elements that just live in the world. But again, this is one where there's a lot of extensions currently, and we expect a lot of extensions to come up that allow you to do things like cube map layers, cylindrical layers, other types of layers that may require more specialized processing or only some runtimes may choose to support. But these two are kind of core and fundamental to the spec. Kind of the last bit of the rendering pipeline is the viewport configurations, and this is something that we actually deliberated on for quite a while, but this is part of what lets OpenXR kind of target everything from camera pass-through AR to stereoscopic VR and AR to something like a cave, which has a lot of projections. Basically, you can query an XR system and say, hey, what kind of viewport configurations do you support? So if you go left to right, a simple case might be one viewport. And if you look at the very bottom, these are all addressed, again, through XR paths, so they're kind of hierarchical. You can say what sort of AR configurations do you support, what sort of VR configurations do you support, and under each one of those, it might have a bunch of different options for it. So, for instance, if you had a Star VR headset, which is a super wide field of view, you might have one viewport configuration that has 2 viewports per eye to let it kind of project around. Or you might have a very simple, just kind of stereoscopic projection that's less physically accurate, but lets you kind of cheat if you don't actually aren't able to render 4 viewports at a time. So basically, applications can decide from the XR system which kind of viewport configurations they want to support, and then they say, hey, I want to use the standard stereoscopic VR HMD viewport configuration, or I want to use a 2 planes per eye viewport configuration. And then it gets to manage that over the lifetime of the session. You can switch back and forth if you want to. You can drop down if your performance isn't able to render as many viewports as you want. You can drop down to more simple viewport configurations. Runtimes don't have as much power as applications in this. They can request that the application change viewport configurations, but the application doesn't actually have to listen to it. And that's because we don't know necessarily that the application can actually support rendering to particular viewport configurations, so the application always has the option to opt out. So this is what it kind of looks like when you call viewport configurations. You pass it a system because we have to know what kind of hardware you're rendering to. We pass it a display time, which is when we think that this frame will be rendered, usually 2 or 3 frames in the future. We ask the XR system, hey, what time is 2 or 3 frames in the future? And we also pass it a space so that if we want to render from the center point between the eyes, or if we have some other arbitrary location that we want to get the viewports relative to, we can just use a space to define those. What that returns is an XR viewport projection info, which has flags attached to it, which such as are the eyes tracked in this for the gaze direction, and that's kind of the only one we have right now. The combined FOV of all viewports, so if you need to do culling and occlusion, you can have that. And then an array of these XR viewport projection infos, which contain a view transform, a projection specification, which is just kind of a matrix and a shear, a gaze direction, if that's not necessarily the same direction that the eye is pointing, and then if it's associated with the left eye or the right eye. So in certain cases, you don't necessarily have one projection per eye. In a case like a cave system where you have stereoscopic planes in front of you on top, left, right, top, bottom, you can have 6 viewports per eye on there, and they'd all be mapped to the left eye because you want that to use the left eye's offset. And you can return as many of these as the viewport configuration has. Right now, the only one that we've encountered so far is a cave, which has 12, but usually you use 1 or 2, depending on if you're doing kind of camera pass-through AR or if you're using stereoscopic VR or AR. Kind of last up in the core specification is how the device plugin itself works. It shares a lot of function calls with the normal OpenXR application side API. You create an instance in order to get a hook to a runtime. But then after that, instead of actually creating a system, you start defining systems. So the XR device plugin connect KHR lets you then start registering things with add device KHR. And devices are basically defining a new system. You use a relative path, usually with my vendor and my device name, and then you specify what kind of functionality that you support. And functionality can be display, trackability, input, haptics, audio in, audio out, wirelessness. That's one of those things that we just kind of leave open-ended. And then once you kind of create that, that gets registered as an XR session that then the runtime can provide to applications. So if you had a new headset, that you wanted to support with the device plugin, you would tell it what kind of features you support. That would register with the plugin. The plugin would register with the runtime, and then any application that connects to that runtime can then say, hey, that's one of the supported devices and choose to use it. It doesn't have to be an entire XR system with controllers and display. You can just register if you have a controller, it can go through the device input. If you have some other sort of tracking mechanism, that can also go through the same function. So once you create and register that system, you set it enabled as long as it's there, and that communicates back up to the runtime. And then through a system of synchronous calls, like display timing info and update poses, you send the information about the device up to the runtime, which it can then process and then reflect up to the application. If the runtime wants to communicate with the device plugin itself, it does through an event queue, which is this XR plugin poll event KHR. And that one, unlike the application level event queue, is expected to be handled within a certain duration of time because we figure that those are performance critical messages that need to be handled. If the runtime's doing something like about to shut down, the device plugins need to know that so they can release their resources. Speaking of extensions, if you're not familiar with how Khronos generally does extensions, we crib this heavily from Vulkan again because they're much older and wiser than we are, and we directly steal all their good ideas. But in the core standard, basically our litmus test for that is core concepts that are fundamental to the specification for all use cases. So things like managing your instance, getting tracking information, and frame timing stuff all go in the core standard. So that means that every runtime that implements it has to implement those things. The next class, kind of next to that, are what we call KHR extensions, which is functionality that a large class of runtimes are likely going to implement. So this is actually something where we put different platform support, so like Windows and Android and Linux and Mac. Anything that's platform specific to that goes in a KHR extension because we expect not all runtimes are going to work on all platforms, so that's something we can't put as part of the core specification. It's also where we put things like the device plugin, where we hope most people will implement it, but there are legitimate reasons where some people might not be able to. That sort of stuff goes into KHR extensions. Next up are EXT extensions, which is functionality that a few runtimes might want to implement, but aren't potentially applicable to all sorts of runtimes. One of the examples of this is the performance and thermal settings, which are kind of based around mobile chipsets to get thermal warnings and performance warnings when you need to throttle up or down your application and helping you do that. That's an example of an EXT extension where we expect a large group of people will be adopting it, but not necessarily broadly across all sorts of platforms. And finally, we have vendor-specific extensions. So if you want to do something kind of experimental, or you want to do something that's very specific to your piece of hardware, you can write a vendor extension which fits into the ecosystem, but isn't necessarily supported across all runtimes. So finally, just a quick note about where we're going from here. As I kind of mentioned, we covered the gray area up to here. Our next step as a working group is to put out a provisional release of the spec, which is kind of a release of the full specification language for people to take a look at, give us feedback on, but that won't necessarily have conformance testing along with it. The next step after that is to define what we want to specify for conformance testing. With OpenXR, it's a little difficult because you have squishy meat beings putting stuff on their bodies and using it. It's a little hard to uniformly test that sort of stuff, so that's where a lot of the kind of mental effort of the group is going to now, figuring out exactly what it means to be conformant with the device plugin API or the application level API. And then shortly after that, once we have an answer to all those tricky questions, we can go through ratification and release the official 1.0 spec, and people can choose to become adopters of it and implement conformant runtimes and put them out in the wild. And with that, that's it. Does anybody have any questions? Thank you. If you have questions, please go to the mic and speak into the mic.
Hello.
Hey.
You might have actually explained this, I might have missed it or something, but so you mentioned the cave that you map everything to the left eye in order to have it all mapped to the left eye offset. Why is the offset not just encoded as part of the view transform matrix? And then it's just like the eye doesn't really, it's like I don't have two, like a left eye and a right eye in some ways. I have an eye that is here pointed this way and an eye that is here pointed this way. And like in a cave, I need cameras in these 6 directions pointed those ways.
Yeah, so it is actually encoded in the view transform in that view projection info that's returned to it. The eye lets the application understand what it's actually rendering to. If it has something like, if you used instant stereo rendering or something like that, it's useful to have pairs of transforms. That's basically where you use one draw call and then use hardware instancing to draw a left eye version and a right eye version.
Interesting. So the term you just used there was a fused?
Instanced stereo rendering.
Stereo rendering, okay. I will look into that, thank you.
For desktop apps that might want to support both like a VR and a non-VR mode, it would be really helpful to be able to, homogenize our interaction with control devices using the XR API. Are you planning to support like a degenerate device that is essentially a 2D desktop window?
Yeah, there's a extension. I didn't explicitly mention it, but there's I believe we call it the headless extension on there, which implies that you don't have a tracked desktop application, but you can run either tracking or device input without having to worry about the render frame or loop, and you can control that as a standard kind of application.
But you're not planning on interacting with like the idea of a swap chain in that case?
You don't have to, no. With the headless, basically, it turns off any functionalities and makes it so you're not required to call and allocate the swap chain stuff if you don't want to, but you can if you do.
But you could allocate a swap chain for like a desktop window?
You could, yeah.
Okay.
You still have to have a compositor that was able to display it, but yes, you could.
Hi, a couple questions. First, what are the IP contribution rules in terms of proprietary IP at the various levels, core and non-core? And then, do you have a provision for an exclusive application versus a cooperative, where you may have multiple in the same space? And then how do you find out how much time you got out of the hardware?
So for the first part, are you interested in the IP restrictions for the different levels of extension? Okay.
So, yeah, if it matters, yeah.
So this is a great question for Neil standing in the back of the room smirking. But the IP zone framework, basically any contributions you make to the spec, you contribute to the IP zone of the specification. So it basically is freely licensed to everybody through the OpenXR standard. You can start to get more and more proprietary and kind of encapsulate your stuff as you get to vendor-specific extensions, but Neil is frantically running to tell me I'm full of shit.
No, you're right. So, but it's the core and the KHR extensions are under the IP framework, which basically, in a sense, says everyone who implements conformant OpenXR agrees not to sue each other. But then the vendor extensions and the EXTs, they're people doing their own thing, so that's not under the IP. Yep.
Thanks, Neil.
And then the exclusive versus cooperative?
Yeah, that's something that's still a little bit under debate. The first bit of that I had mentioned that XR session went from being a handle lifetime object into a begin and end session. That's part of the discussion that we're trying to suss out exactly what we're going to do on that. So TBD, unfortunately.
Hi, I'm curious about the action sets. Does that imply that there's like one active one and I have to swap between them, or can there be multiple active? Because I'm worried about the combinatorial explosion if I want to be like flexible.
Yeah, so there's you don't have to use action sets. There's a standard global action set where if you say this is just all the stuff I care about and I want to handle that in my application, you can do that. Freely, but you can use action sets, and I think the only restriction on them is you can't have an action that's in more than one set at a time unless you put it in that global action set, because when you destroy an action set, it destroys all of its children per the handle lifecycle rules, because those XR actions become children of their action sets.
Thanks.
Yep.
In terms of what you're cribbing from Vulkan, are you also I think it's great. Are you also targeting the machine-readable XML representation of the API to make it easier to create alternate language bindings?
I'm not super familiar with that part of the Vulkan specification. Yes, Carl would know. So yes.
And You touched tiny bit on audio when you were talking about the device plug-in side.
Yep.
One of the things that I've seen kind of like as chaotic in the VR space is, what do you do when somebody puts on a headset? Where does the audio for the application go? How do you communicate that to the system? Say, hey, switch to this audio device. Are you going to be focusing on that in the API?
That's still one of the open questions. The device plugin is one of the last things that's kind of being formed and coming online. So we have the specification for whether or not it supports audio in and out on the plugin device API, but the lifetime and whether or not it would be routed to the actual device itself is probably part of the session, which is still being debated on how specifically that's going to be handled. But it is something that we're taking into consideration because it is something of a mess.
Thank you.
Just a small question about the action system and the bindings. So you said that applications can suggest for known devices bindings. Is that a per action thing, or can you suggest groups of actions in sets? So you could have profiles. If A does X and B does Y, that works. But I want to provide those two together as a suggestion as opposed to independently.
Right now, in the spec in its current form, it's by action, so it's not per action set.
Okay, thanks.
Hi, I have a question about the frame life cycle. Do you specify in any way like the moment in time when compositor is working so that application is notified that in this moment in time you shouldn't do any DMA transfers or anything that could trip the compositor?
That's part that's kind of implicit in the XR end frame call. We say that we're not going to submit any draw call commands, so it's up to the compositor to look at how long he thinks the GPU work will take and then slot in by there. But we expect that most runtime authors, kind of like they do now, will use some of the preemption APIs potentially to reproject a frame and display it if the application is taking too long on the GPU.
Okay, but I was thinking about like if application is spawning in the background, like transfers of data on PCI, that could trip the compositor if compositor needs to suck in some data at the PCI as well, and it's now queued behind huge data transfer.
So you're talking about external applications hogging the GPU or something?
Yeah, or even just rendering at the same time when you transfer data, right? But like you finish your rendering in time, before the deadline, compositor can pick that up, but now you trip the compositor because you still transfer textures or something.
Yeah, that's the problem of having multiple applications run. It's something that we leave largely to the compositor in order to set up the timing of it. We can't force other applications not to do something on the GPU, but different runtimes have different methods for mitigating that as much as possible. So we don't explicitly set anything in the specification regarding that, but we hope that the timing information that we do provide the runtime from the application with the begin frame, end frame, and wait will let the application at least do something intelligent if it keeps getting preempted on the GPU, maybe throttle the application down to every other frame so that it has a larger window with which to try to fit its work.
And by begin and end frame, you only gate like a workload dependent on the pause or the whole workload of the frame?
Sorry, I couldn't hear you with the door open back there.
By begin and end frame, do you gate like only the workload that is dependent on the pauses, or do you also take into notice like pause independent workload that could happen immediately?
Just the stuff right now that's taken from the application between the two calls.
Okay, thanks.
Yep.
Hi, I'm just curious, to what extent might an understanding of world geometry become a part of the spec for platforms like HoloLens and Magic Leap?
Well, so ingesting like sensor data from there.
Yeah, like a world mesh or even semantic understanding of the world?
Right now, there's nothing specified in the core spec, but that's something that would probably target a KHR extension since there's a wide class of devices that will support that. But as of right now, we aren't ready to announce anything specifically about that. All right, any other questions? Oh, Ben.
Hello.
Hey.
It's me. If you were to have somebody who wanted to do gesture input, like a circle should be a button press or something, is would you advise that being specified by the device, the application, or is there any support even in that for in OpenXR?
So that would probably be something that the application would devote an event to for whatever it was actually listening for that, and then that would be the suggested binding. If there was a gesture input API that the runtime supported, they would bind the circle gesture to that, which would mean that, you know, if you had maybe a, you know, something that had hardware specifically for recognizing that gesture, it could send it, or if you had a motion controller or something in the runtime wanted to record the position and then fire off gestures as part of the input system, it would then be free to do that. That makes it a little more future-proof and versatile, I think.
Okay, and then if the device creator wanted to, could they just contain all that within the device logic itself and just have it output, you know, it did a circle, and so we're going to pass a button press?
Yeah, you could just bind that as basically one of the, a semantic path that was my input gesture or something, which the runtime would then present some UI to the user that could say, bind the circle gesture from my magical gesture recognizer device to cast a magic missile or something.
Got it. Thanks.
Cool. All right, thanks everybody.